Welcome to the Purdue Nanophotonics Lab. Here at Purdue, we develop materials with feature sizes much smaller than the wavelength of optical light. These artificially designed structures act as artificial atoms, enabling optical properties beyond that of any naturally occurring material. The Greek prefix meta means beyond. For this reason, we call the materials exhibiting optical properties beyond anything that can be found in nature metamaterials. Just a few of the materials developed in our lab include materials with a negative refractive index, materials that provide super resolution, invisibility cloaking, and optical black holes. When light comes in contact with a naturally occurring dielectric material, such as glass or water, light will always bend at a positive angle. We refer to these materials as having a positive refractive index. However, by using small amounts of metal with a carefully designed structure, light will bend at a negative angle, having a negative refractive index. We refer to these materials as negative index materials. Refractive index is a fundamental property of optical materials, and its implications go far beyond simply refracting light in a different direction. Because many objects, such as DNA and viruses, are much smaller than optical light, information about the structure of these objects cannot be seen using conventional optical methods. By using a negative index material as a lens, we can perfectly recreate the image of an object on the far side of this lens, no matter the size. By making this lens with a curved geometry, this lens can be attached to any conventional optical microscope, providing near-perfect resolution. Invisibility cloaking is another exciting application. While light usually propagates in straight lines through materials, we are able to artificially engineer the optical space using metamaterials, causing light to travel in an arbitrarily designed path. Stretching the optical space creates a void in which light will flow around, just like water flows around a rock in a river. An observer would see whatever is behind this void, rendering an object inside completely invisible. Rather than bending light around an object, the optical space can be collapsed, continuously pulling light towards the center. Light passing near enough to this material would be pulled towards the center and trapped. Because this material traps all light passing close to it, much like a black hole, we call this an optical black hole. Negative refractive index materials, super-resolution microscopes, invisibility cloaking, and optical black holes are just a few of the exciting applications we are working on at Purdue University's Nanophotonics Lab. You can find more information about our work online. Thanks for watching.